So when last we left, we had discovered that batteries store not charge, but energy, electric energy. And they get that by they're a chemical reaction that moves the electrons from one side to the other side. And if you have a whole bunch of negatives all piled up on one side, what do those negatives do to each other? They repel. They're like, I don't want to be near here, and they're desperately trying to get away. So if you were to connect, and if these electrons have moved over here, what did they leave behind on the left-hand side? They left behind positives, okay? Not that there's not positives all the way through, it's just that there's more electrons over here and less electrons over here. So what will happen is the electrons will say, I don't want to be near the other electrons, but I can't get back because the chemical reaction is pushing me that way. So if we attach a wire, then the electrons can go through the wire to escape the other electrons. And in the meantime, this wire is full of electrons, right? It's not like the electrons just start here. There's electrons because wire is made of atoms. And atoms have, what do atoms have? They have electrons. So all the way around there's electrons. So the moment that this one, if I attach the wire there, this one pushes out and it pushes all the others along. And at the same time, these positive charges over here are pulling the electrons in. So there's a pushing and a pulling that's going to cause those electrons to flow. Okay? All right, we'll carry on from there. Basically, what's happening is you've run out of reactants in your chemical reaction. Okay, once that happens, there's no more chemical energy, and your battery is dead. Okay, so what we got over here is we have a little cylinder which is made of zinc powder which has been compressed together to make a cylinder. On the other side, we have a hollow cylinder which is made of manganese oxide and carbon. And let's figure out where the electrons want to end up. So in this reaction, the electrons would rather be with the manganese than with the zinc. But in the process, through the wire, that also pushes the electrons along. What happens to the speed of those electrons moving as the battery runs down? Yeah, they go slower. So let's just take a look at what they were like before, and then what happens when the battery runs down. See how they're moving slower now? Did you guys catch that? The zinc cylinder goes inside the hollow manganese oxide cylinder, and then they put the casing around it, and that is your battery. And there will be an alkaline solution in there, okay? So let's just go back and watch that happen one more time. There's our one reactant, there's our other reactant. Let's watch how they come together. Does anybody know what the unit of energy is? You're close. That's actually energy per second. Yeah. Volts is energy per charge. Joules. Energy is joules. And we'll come to those units a little later on. That's how we spell joule. But it sounds kind of like the word Jewel, joule. Okay, because we just pronounce them both with one syllable. Okay, so we have bulb A over here. Do you see how its little glowy thing is smaller than for bulb B? Yeah. That's going to be because of the actual design of the bulb itself. Some bulbs will give off more energy in a given time. Okay. Which one do you think would use up the battery faster? The less glowy one or the more glowy one? The more glowy one. It uses up energy faster because it's glowing more brightly. I think we just determined that. Which one would run the battery down slowest? The one on the left. Very good. So we have these two batteries are running light bulb A, and these two batteries are running light bulbs B and C. Which one is using energy faster? The right one. The two bulbs use energy faster, so your battery will wear down faster. So if it's supplying energy twice as quickly, what can you say about the amount of time the battery will last? Half as long. Yeah. I don't know if you guys can hear it, but the teacher who recorded this, every once in a while she goes, It's kind of cute. Okay, and that concludes lesson 1 for that. So we're just going to set that on pause. And we are going to go to page 1 of our new workbook. Hey, is this updated? Let's sync this puppy. Sync notebook now. Where's my electricity? Oh, that sucks. Okay, that's all right. I thought I was sure I had, okay. Fine. We can make it work. We'll go to fall, sure. And then we'll go to electricity. There we are. No, not that. Electricity. Yay. Okay. Actually, we're not going to be on page 1. We are going to be on page 3? 6. We're on page 6. Or no, I think we're on page 3. Are we on page 3? It doesn't say the numbers? Oh no. Okay. That's awkward, but we'll make it work. We are on 6.1a, so find the first page of 6.1a. That's my bad. I must have messed up on that. I was trying desperately to get this out to print. Okay. Has everyone found this page? First page of 6.1a. A pencil, yes. Right there. Okay. So previously in our chemistry unit, we learned about 3 types of bonding. Okay, good. Where's the lid? That's a really good question. Previously in our chemistry unit, we learned about 3 types of bonding. Tell your partner what the 3 types of bonding are. You might only remember 2, but there is a third. Okay. 3 types of bonds. Number 1, ionic. What kind of elements are involved in ionic bonding? Metal plus nonmetal. Number 2, covalent. What kind of elements are in covalent bonding? Nonmetals. And number 3, is the one we didn't really learn much about. Metallic. And this is metals only. Okay, so we're going to watch a little video about metallic bonding, but just before we do that, we're going to do a little learning about it first. Metallic bonding. Do you remember the words electrostatic attraction? Describe to your partner, what is electrostatic attraction? Oh yeah, for sure. In electrostatic attraction, what things are attracting each other? Positive and negative. Sorry. Okay, electrostatic attraction is the attraction between positive and negative. So often, in this particular case, when we have metallic bonding, the positive things are the metal cations, and the negative things are the mobile valence electrons. What does the word mobile mean? Moving. So this is the key thing about metals. Their valence electrons do not stay locked on their home atom. Okay? When you have ionic bonding, everybody's electrons are locked in place. It's like these ones belong to sodium and they stay with sodium. These ones belong to chlorine and they stay with chlorine. In covalent bonding, whoever owns those electrons, even if they're sharing them, those electrons do not move. There's some exceptions to that you'll learn if you take some enriched chemistry, but for the main part, electrons do not move, except if we have metals. If we have metals, those valence electrons can actually be like, oh, here I am in atom A, but now I can move to atom B, and now I can move to atom C, and they just kind of push each other along, okay? So metals have giant structures. Can you please not talk? Metals have giant structures very much like a crystal lattice. In fact, they are crystal lattices. They are metallic crystal lattices. Uh-oh, page has stopped moving. There we go. Oh, cancel. Okay. Crystal lattices. So what does that look like? Well, when we had an ionic crystal lattice, what did that look like? We had positive, and then we had negative, and then we had positive, and then we had negative, and then we had negative, and then we had positive, and then we had negative, and then we had positive. Alternating, yes? Now, in a metallic crystal lattice, what we have is we have the atom, we have its nucleus, we have its core electrons, and then we have its valence electron. Okay? So what happens is that the core, the nucleus plus the inner electrons, gives us a cation. Right? If we ignore that one valence electron, if that valence electron were not there, this would be Na+. Does that make sense? If that electron, if we ignore this electron, we get Na+. And Na+, that is our nucleus plus the inner electrons, and that is the cation. okay? So each of these little balls in this little model here is a cation. So they are all positive, 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 positive. Does anybody see a problem with a structure that just looks like that? They would repel one another. So there must be something in between the cations that is negative so that they will actually stick together. So there has to be something between the cations to stick them together. What charge does that something have to be? That something has to be negative. So there must be something negative between the cations to get them to stick together. Now remember, our cations, that's the yellow part of that diagram, right? What's the part that we were ignoring? We were ignoring that valence electron, right? And guess what valence electrons are? Valence electrons are negative. So in between all of those cations are those negative electrons, okay? So there will be valence electrons. Valence electrons. But remember we said they are mobile. So you can see they've all got little red arrows. They're moving all over the place. All right? But they're in between. So this positive ion is sticky. It attracts to that negative. This positive attracts to that negative. And it doesn't matter that it moves because there's always another electron coming in to take its place. Yeah? Because there's thousands of electrons, not just a few like we see here. So we call all those electrons that are in between, we call it a sea of electrons. I don't mean a sea. I mean a sea, like the ocean, okay? So we call that a mobile sea of electrons. So let's write that down here. It is written there, but let's make it big so you don't miss it. We have a mobile sea of valence electrons. Since those valence electrons don't have any one particular home, they're free to move from here to there, from this end of a wire to that end of a wire, we say they don't have a specific location. So we can say that they are delocalized. The valence electrons are delocalized. So that's a vocab word. There will be a quiz on metallic bonding sometime in the future, probably 2 days from now. I'm guessing today's Tuesday, so maybe Thursday. Okay. So the valence electrons are delocalized. So we have a mobile sea of valence electrons. Those electrons are delocalized. And delocalized means not stuck in one location.
Oh.
And I think this is something I wrote last year because I don't remember writing it this year. The negative electrons glue the positive cations together. And I have a model of this somewhere. Oh, there it is. Okay, this is a model of metallic bonding. This is just a little Tupperware container sort of thing that I got from home. Inside here are some styrofoam balls because they looked round and they were cheap. Okay, got them from the dollar store. And surrounding those styrofoam balls is corn syrup. Are you guys familiar with corn syrup? Yeah. If not, it's kind of like honey. It's sticky, it's gooey. It is what they put in Coke, high fructose corn syrup, okay? But I had some corn syrup kicking around, and so I used it for this because it was sticky. And the thing about it, it's a liquid, so even though it's gooey, it will flow. Yeah? What do you think the styrofoam balls represent? Cations. Those are our cations. What do you think the corn syrup represents? Those are those electrons. I would love it if I could take this and open it up so that you can see if I push down on it, because all the corn syrup can flow, it's not going to break. Like if I hit it really hard, if I could open it up and hit it really hard, it won't break, it'll just spread out. Do you remember that metals, what happens if you hit them? They just dent or deform. And that's because the corn syrup allows them to spread out. So it's not brittle. Okay? Do you guys remember that word? Malleable. Okay? So it is this mobile sea of electrons that allows metals to be malleable, because the corn syrup doesn't care if you smush it, it just stays in between the cations. And so they still stick together. Whoops. All right. Why do mobile electrons give up their valence electrons to this C? Why don't those electrons stay on their home atom? This is an enriched thing. Metallic atoms have a low electronegativity. And things with a high electronegativity pull on electrons strongly. And if you're interested in why, you can take Chemistry 11, okay? If things have a low electronegativity, and you'll see why when I get to grade 11, we just start calling it EN, because that is one heck of a long word, okay? If you have a low electronegativity, the pull on electrons is weak. Nonmetals tend to have high electronegativities. Metals tend to have low electronegativity. So the metals are kind of like, there's an electron out there in my outer shell. Do I care if it moves to another one? No, not really, because I'm not pulling on it very strongly, right? And neither is the other one. So they're just free to kind of move around. And if that metallic atom, if the metallic atom loses its outer shell electron, the cation that's left behind, what can you say about the outer shell of the cation? What can you say about the outer shell of this cation? It's lost its valence electrons. What can you say about that outer shell? What's special about that outer shell? It's full. And full outer shells are stable. Okay, so in the cation, the outer shell is full, and full outer shells are stable. So not only do they not hold on to their electron very well, they become very stable when they let it go. Okay, so then they're like, oh, I like not having this electron attached to me because I'm very stable with my full outer shell. And then those electrons just go roaming all around. So here's a picture of all of the sodiums, sodium cations. And we have the valence electrons. And they do move around, but what you can see is what I've drawn down in here is I've drawn some little dashed lines. Do you see how I've highlighted them there? I'll unhighlight them and highlight them again. Okay, down here, this negative charge is attracted to this positive charge. That negative charge is attracted to the positive charge of the other sodium. And that negative charge is attracted to all the cations around it, all of them. So that's actually quite a strong bond because it's almost like a spider web where it's like, ooh, I stick to this and this and this and this. Yeah. And if we were to draw other ones, we could say, okay, I also get attachments here and here and here and here and here and here. So do you see how everything's really glued together? That gluing together is our electrostatic attraction. It's the electrostatic attraction between the positive cations and the mobile negative electrons. Okay, so if you want to add that in, it is the electrostatic interactions, which are attractions, between positive cations and the mobile negative electrons. This is just another diagram. I don't know why I bothered showing this one when you have another diagram up here, but this is the attraction. Attraction. And remember, those electrons are mobile. What does mobile mean? Mobile means they're moving. And they are delocalized, which means they are not stuck in one location. They are movable. And just in case you guys are interested, I had one of my Chemistry 11 students had seen your answer key on the back counter, and she's taking Physics 11 right now. And she's like, do you have the workbook for this? Can I borrow one? Because she's doing Physics 11 right now. So apparently she just wanted like a little brush up on the concepts of like electricity. And she was like, this looks good. Let's use this. So if you do take Physics 11, this will probably come in handy. Okay, so all of the stuff in this unit. All right. Are we good? Anyone need more time on that? Or are we moving on? We're moving on. Okay, good. So here is another image, and this is like a time-lapse photography. Do you see how if we had them moving all over time, it would be like this sea of electrons. They'd be just spread out everywhere, all around them, in front and behind, et cetera, et cetera. Okay. Now, this next bit is enriched, and I feel like I've talked a lot already. So you can feel free, if you want the enriched part, to read that. Okay. We are going to, though, skip ahead to page, I don't know what page, because apparently it doesn't have pages. So we're going to go to the one. So just keep flipping until it says 5, good conductor of heat. Anyone not find it? Look for where it says 5, good conductor of heat at the top of the page. Okay. So this stuff here is regular. Okay, this is non-enriched. Pages before this are enriched. Okay, but this is not enriched. Imagine you've got a fire happening over here on one end of the wire. Okay? If those electrons were not mobile, they could only speed up nearby ones by banging into them by vibrating. Yes? Like if they were just vibrating, they'd be like bang, bang. But if you have mobile electrons, this electron can go bash. Whoa. And then the other electron moves faster. Ooh, faster. Faster, faster, faster. So this electron moves faster because of the fire. That says cuz. And then it goes bash into the next electron. And that electron moves faster because it just got bashed into. And what that means is that you can get heat, which is, heat is basically just particles either moving faster or slower, depending on what they're in contact with. The heat can spread from one end to the other very quickly because the electrons are moving and they can pass on that energy all the way to the end of the wire. So do you remember when we said that metals are good conductors of heat? That's because those electrons transport that motion from one end of a piece of metal to the other end of the piece of metal. Also, why are metals good conductors of electricity? It's because the electrons can move easily. Conductors need moving charges. If you have, let's just say we had some dry ice, some carbon dioxide. Those are covalent bonds, right? And the carbon and oxygen, those nonmetals together. Everybody's electrons are locked in place. Are there any charges that can move in the CO2? No. And that's why CO2 cannot conduct electricity. If you had some dry ice and you put some wires on it, it would do absolutely nothing. But if you have a metal, because we have these mobile electrons, and because our positive attracts negative, in this diagram, let me get rid of all this nonsense here, and then we can go back. Anybody taken like electronics or anything like that? A few of you? Okay. If you've not taken electronics, this little symbol down here, this one here, that has a plus and a minus, that represents a battery. Okay, it's actually a cell, but we're not going to get too excited about that differentiating that this year. Okay, that's a battery. And if batteries have a positive terminal and batteries have a negative terminal. Now, I don't know how you want to remember this, but the small one is always negative, and the big one is always positive. For me, in my brain, I'm like a negative is made of one small line. Yes? If I take the two lines in the plus and I put them together, I get a big line. I don't know. That's how I always think about it, but you'll just have to remember negative is smaller, positive is bigger. But if you think about a number line, maybe that works too. Negative is smaller, positive is bigger. However you remember it. Anyway, we got a battery there. And remember, we've got this positive charge here in our battery caused by that chemical reaction. What does that positive charge do to all the electrons that are in the wire? What does this positive do to this electron? Yes, it attracts it, okay? And it just keeps pulling them along. And then on our other side, we still have electrons all throughout the wire. What does this negative do to those electrons? It repels them and it pushes them along. And so we get a flow of electrons through that wire and they can move because there is a mobile sea of electrons. Okay, and I think that's it for that. We're going to watch a quick little video just showing us how delocalized electrons allow current to flow. Now remember, we kind of like gave up on things after element 20. Technically, you can kind of draw a Bohr model with 18 things at 18 electrons in the third shell, but we're not going to worry about that because, like I said, Bohr model breaks down. Okay, and that's that. Okay, we're not going to watch it again. Okay, and now there are some questions here. We have 20 minutes left, so I think you could do page 12 and 13. Yeah. Yeah. Quiz on this on Thursday. Is this page 10? Thank you. 10 and 11? 9, 10? It's the question. Do the exercises for 6.1a. Thank you. And if you wanted to be really clever, at some point you could number your own pages. I'm so sorry that I forgot to get the numbering on there for before it was printed. Just do the exercise. Yeah. Yes. Yes. Afghan. What's up? Oliver. So we did our test yesterday. I think you'll be able to put lots of So, that's like not such an important factor. Great. Yes. They are like.
Oh,
Yes.
What do you think that should be?
Thursday. Thursday.
Right,
You get a bonus mark. Oh, yes. Yeah.
Remind them.
Okay.
So.
Yeah. Just cut your knocks off. Yeah.
Where do you go? Yeah.
This place, can I go? You don't make food.
Yes.
Oh, to.
Well, that's right.
Yeah.
Yeah.
That's the last thing.
Oh, right.
Yeah, I don't think it will be right. Oh, it's always wrong. It's wrong. Just call it. Yeah, so yeah. We don't have to see it. You're worried. Then like why would we see like
Yeah. Armando, you didn't finish a quiz on chromosomes. Yeah.
No, I did. Oh my God. Oh. That's, it's not like, I want to see, it's not.